So students, welcome back to one more session of your Bohr's model of an atom. So we have seen how Bohr has given the hydrogen spectrum, isn't it? Right? So in that hydrogen spectrum, we have clearly seen the different series, that is Lyman series, Balmer, Paston, Brackett and Prefun. So now we are going to learn the concept called Bohr's model of an atom. So here, after Rutherford's model, so what does Rutherford give us? Rutherford stated that atom had a nucleus, right? And he said electrons were present outside the nucleus. So he could not say anything that he could not speak anything about the electron arrangement in an atom. So here in 1913, Niels Bohr, okay, this person Niels Bohr has given us a new model of an atom. So new model, he has clearly explained about the different orbits where the electron is moving. So let's see what actually did Bohr said. So Bohr, first of all, whenever you're given a question in the exam, first you need to write the postulates of Bohr. What did he say? He said, already we know the concept that electrons are revolving around the nucleus. So he said, suppose if I take a particular atom, so center you have your proton, okay, and the neutron also present in the nucleus. Okay, let me draw shells, not round enough, but okay, not a problem. Yes, so I'm sorry, this is not at all round. My God. Okay, done. So let us name this as 1, 2, 3 and 4. Okay, now let us start with the first postulate. What did Bohr say? The first postulate, he said electron always travels around the nucleus. So electrons are here present in each shell. Okay, so first postulate of Bohr says electrons travel around the nucleus, in specific permitted circular orbits. This is one circular orbit, this is one more circular orbit, this is one more circular, and this is one more circular orbit. So permitted circular orbits. Okay, orbits, that is what. Fine. So, and no other. So they're fixed in this part, this part. Now, the second postulate he said is, when they're traveling in the specific orbits, an electron does not radiate energy. So let us write that. While traveling in these orbits, the electron do not radiate or lose energy. Okay, they're not going to radiate or they're not going to lose energy. That's fine. That's over. They're traveling, they will not lose any energy. So the third postulate which he gave was an electron can move from one energy level to the another energy level, from here to another energy level. While it has to jump from here to here, it has to absorb one quantum of photon of energy. So let us write that an electron can move from one energy level to another, and during this process, what does it do? It has to absorb one photon or one quantum of energy, and absorbs one photon or quantum of energy. One quantum of energy. That's it, right? So now this is your concept. So basically these are the different postulates which Bohr has given. But now we spoke about one photon or one packet of energy or one quantum of energy, isn't it? Right? So how is this the quantum or the photon of energy absorbed? So from lower energy to higher energy, it has to jump, it will absorb. When it is jumping back from the higher energy to the lower energy, it's going to emit, isn't it? Now the absorbed or emitted energy or the quantum of energy, we are going to denote it by just now delta E. So suppose if it is jumping from lower to higher, it will absorb. From higher to lower, it emits, is it? So that's denoted by change in energy is denoted by delta E. Delta E is equal to E higher energy. Now it is emitting minus E lower energy, so it's emitting. So this is equal to h nu. Okay, now what is h here? H is your Planck's constant, and your nu is your frequency. Okay, frequency of a photon emitted or absorbed. Okay, yes, so this is or absorbed. This is what is the concept. Fine. So now like the fourth postulate, if I have to say, a very important postulate, the angular momentum. So what is angular momentum formula? That is mvr, isn't it? Yes. So now this angular momentum, when the electron is revolving in circular orbits or fixed orbits, the angular momentum that is mvr of an electron, angular momentum of an electron, yes, is an integral multiple, is an integral multiple of Planck's constant, integral multiple of Planck's constant divided by 2 pi, divided by 2 pi. Okay, that means your angular momentum, what is that angular momentum of that electron? Angular momentum is denoted by mvr, which is equal to nh by 2 pi. Okay, we written, isn't it, is integral multiple of Planck's constant divided by 2 pi. Now what is this? This one, m stands for mass of electron, nu stands for velocity of electron, r stands for radius of the orbit. Now n is equal to, it can be 1, 2, 3, etc. h is a Planck's constant. Fine. Now if you put the values of 1, 2, 3, if you put the values of n in this becomes what? Now if I substitute, this becomes h by 2 pi if n is equal to 1. Then if n is equal to 2, this becomes 2h by 2 pi. If n is equal to 3, this becomes 3h by 2 pi, etc. Isn't it? Yes. So there can be any fraction value for h by 2 pi. Remember that. So that now the angular momentum is said to be quantized, isn't it? This value is quantized, as you have seen. Fine. So this is also, that n is called the principal quantum number. Basically, when you learn the quantum numbers, you will just see what actually is principal quantum number. So Bohr, now he said, first postulate, he said electrons travel around the nucleus. Second, he said that electron travels in fixed orbits around the nucleus. After traveling, he said one more thing, while they are traveling, they do not radiate or lose energy. Because they do not radiate or lose energy, they will not fall into the nucleus, isn't it? Then he said an electron can move from lower energy to higher energy by absorbing a photon, or it can travel from higher energy to lower energy by emitting photon, right? So this is what. Then the last but not the least, he said the angular momentum is equal to mvr is equal to nh by 2 pi. It is quantized, isn't it? That n value, it will be equal to 1, 2, 3, etc. Fine. So with these postulates for Bose of an atom, he has given a formula for calculation of radius. So let us write calculation of radius of orbit, radius of orbits. So what did he give? This calculation of radius of orbits, what did he give? He said, let us see how he is calculating. First, let us assume this around, fine, the center nucleus, yes, right? So from here till here, let me mark it as, this is the radius, isn't it? Now I'm going to draw a line. Now this is mv square by r, the centrifugal force. Now the quantity which is acting is the velocity. Now what is this? This is the force of attraction between the electron and the positive proton. Now this is Zt. Now let us explain this. So how did he explain the radius of the orbit? First of all, he said consider an electron of charge E. Okay, there's one electron of charge E. Right, it's revolving around the nucleus, okay, of a charge is Zd. The charge of electron is E and the charge of the nucleus is Zd. Now what is Z? Z is basically the atomic number of the particular thing, and E is the charge of proton. Okay, let us write what it is. Basically, I said there is an electron of the charge E, okay, E, and we have a nucleus of charge, like nucleus, in that you have a proton, that is small e. Okay, yes, fine. Now Z is what? Z is the atomic number. Z is the atomic number. Fine. Now what is N? Now let us assume M be the mass of electron. This M be mass of electron. Now what is R here? R is the radius of the orbit. Radius of the orbit. Now what is this nu? Nu is the tangential velocity of the revolving electron, this nu. So nu is a tangential velocity. We are trying to calculate radius of the orbit. Tangential velocity of revolving electron. Revolving electron. So hope all the quantities are there in the formula. Yes, let's see. First of all, I have said Z is atomic number, E is the charge of the proton, R is the radius, then we said E is the charge of the electron, this is the tangential velocity, M is the mass of the electron, okay, velocity, radius, that's fine. So now let us write the formula. We'll see how radius is calculated. So now basically according to Coulomb's law, okay, according to Coulomb's law, the electrostatic force of attraction between the nucleus and electrons. So according to Coulomb's law, electrostatic force of attraction, they always exist. Electrostatic force of attraction, isn't it, between nucleus and electron. So it's given by ZE into E by R square. Now you have one more thing which is acting, that is your centrifugal force. Centrifugal force acting on electron, okay, acting on electron, that is equal to mv square by R, both the things. Now Bohr assume, what does he assume? This force and this force are acting opposite to each other. So when they act opposite to each other, then only it will hold that electron around the nucleus, isn't it? So he said both are opposing forces, they balance the electron and they maintain in the orbit. So he has equalized these two. So Z squared by R square is equal to mv squared by R. Now for hydrogen atom, for hydrogen, Z is equal to 1, isn't it? So what will this formula be? E square by R square is equal to mv square by R. Now we are going to multiply both sides by R. What do we get? We get E square by R is equal to mv square. Fine. Now according to Bohr's postulates, what did we learn? According to Bohr's postulates, we said angular momentum is of the revolving electron. We said mvr is equal to nh by 2 pi, isn't it? So we said mvr is equal to nh by 2 pi. Now take out that nu out. Nu is equal to nh by, this comes down, 2 pi mr. Now new value I'm going to substitute in this case. See here, I can substitute this value in this case, isn't it? So what do I get? I get E square by R is equal to nh by 2 pi mr whole square. Now I'm going to solve it for R, right? So I'm solving for R. So now I'm going to solve. So this comes down. So R is equal to n square h square by 2 becomes 4 pi square, m becomes m square, m, okay, this m and this m gets cancelled, isn't it? So m and E square. Fine. So since now we know the value of H, Planck's constant 6.6, then we know the value of mass of electron, right? We know the value of charge of electron. So what do we get when we substitute, right? We get R is equal to n square into 0.529 in 10 raised power of minus 8 centimeters. This is what we get. Now if I take n value is equal to 1, then R will become equal to 0.529 into 10 raised power of minus 8 centimeter. So this is your Bohr's radius. Okay, Bohr's radius, and this is also called as alpha naught. Fine. So alpha naught is called the first Bohr's radius, because we have taken n is equal to 1 here, n is equal to 1. So this is called, alpha naught is called what? Bohr's first radius. First radius. Fine. So this is how you're going to calculate Bohr's first radius. So let us do one numerical, and with this your Bohr's atomic model is done. So let us write the numerical. What is that? Calculate the first five Bohr's radii. Okay, first 5 means n is equal to 1, n is equal to 2, like that. You need to take applying in the formula. Fine. Bohr's first radii. That is what. Fine. So let's see. So what is the equation? First, calculate the first 5 Bohr's radii. Formula is what? R is equal to n square into 0.529 into 10 raised power of minus 8 centimeter is the formula. Now first 5 they've asked me. First 5 means n is equal to 1. Then this becomes R is equal to 1 square into 0.529 into 10 raised power of minus 8 centimeter. Fine. Now n is equal to 2. R will become 2 square into 0.529 into 10 raised power of minus 8 centimeter. Now n is equal to 3. Then n is equal to 3 means this becomes R is equal to 3 square into 0.529 into 10 raised power of minus 8 centimeter. Now n is equal to 4. I need to find till 5, isn't it? R is equal to 4 square into 0.529 into 10 raised power of minus 8 centimeter. N is equal to 5. R is equal to 5 square into 0.529 10 raised power of minus 8 centimeter. If I solve, I get here 0.529 into 10 raised power of minus 8 centimeter. In the second case, I get 2.12 into 10 raised power of minus 8 centimeter. In the third case, I get 4.76 into 10 raised power of minus 8 centimeter. In the fourth case, I get 8.46 into 10 raised power of minus 8 centimeter. In the fifth case, 13.2 into 10 raised power of minus 8 centimeter. Fine. This is how you're going to calculate the radius for the Bohr's orbit. Fine. So applying in the formula. Now I hope the concept is clear, students. So next we are going to study about energy of electron in each orbit. So this is again your Bohr's the same concept. Let's come back and see the next one. Right. Now, after calculating the radius of Bohr's, he has given us a concept called calculating radius, isn't it, of the Bohr's orbit. We've also seen alpha naught, that is radius of the first Bohr's orbit. Now, after that, the second important thing about the structure of atom, energy of electron. Right. Now let's come back and see how Bohr has calculated the energy of electron in each orbit. So we have learned the radius, isn't it? Now that is what the heading is. Now basically for hydrogen atom, right, hydrogen atom, the energy of the revolving electron, how is this given? Energy of revolving electron is E. Right. Now what is E equal to? E is equal to sum of kinetic energy plus potential energy, isn't it? Yes. Now what is kinetic energy equal to? Kinetic energy is equal to half mv square, and potential energy is the value is minus E square by R. This is your potential energy, isn't it? Now so let us write. Now E is equal to half mv square minus of E square by R. Now from the first equation, the earlier one, what did we get? We have got mv square is equal to E square by R, isn't it? Yes, this is, we've got this. So now what are we going to do? We're going to substitute the value of mv square in this case. Yes, so let's take this and substitute in this formula, mv square, this particular thing. So here what do we get when you substitute? E is equal to half, okay, I'm substituting this value here. Half is here, m is E square by R, that is equal to minus E square by R. Okay, now E is equal to minus, so half, and this one, this becomes minus E square by 2R. Yes, fine. So now we're going to substitute the value of R from equation. Now we have the value of R already got in the earlier video, isn't it? So that value of R I'm going to substitute. E is equal to minus E squared by 2 into 4 pi square me square by n square h square. This becomes equal to 2 pi square me, 2 and 2 gets cancelled. So 2 pi square me divided by n square h square. Now substituting the value of m. Now I'm going to substituting the value of m, value of E and value of H in equation 9. So what do I get? E is equal to minus 2.719 into 10 raised power of minus 11 by n square, or by atom. The same thing, you can write it as E is equal to minus 2.719 into 10 raised power of minus 18 by n square joule per atom. Or you can write the same as E is equal to minus 131.8 by n square kilojoules per mole. The same thing, you can also write it as E is equal to minus 313.3 n square kilocalories per mole. Okay, all these are there. So by using proper integer of n, you can do this. So this is your Bohr's model of an atom for calculating your energy of orbit.